In this tutorial, we'll use a couple of different plugins to create this panelized tensile structure. We'll start with Voronoi diagram to get the curves, then expand the mesh and let Kangaroo do its magic. Later on, we'll use a special plugin called Striper to get mesh strips along defined direction, lift internal points, and lastly, map our tiles and give it some coloring with gradient components. Let's get started. First, I'm going to create point container and I'm going to reference point inside Grasshopper. This point will be used as origin of XY plane. This guy I'm going to use as a base plane for the rectangle. And here we'll type X and Y direction. Once we create the rectangle, I'm going to populate with a random point. So I will use component populate 2D and I will populate with 10 points. Set the seed number, let's say 71. And once we create a random point inside the rectangle, I'm going to generate Vertex diagram. In the next step, I'm going to trim these Vertex cells. I will use component trim, so the cells or the curves that are going to be trimmed are the Vertex cells, and the region to trim against will be this rectangle. I will extract only the curves inside. Here, once we trim these curves, we have overlapping curves. As all these lines are point lines, so for instance, this is one point line, this is second point line, and here we have overlapping lines. First, we need to explode these point lines. I will take their segments and I'm going to flatten the list of segments. I will extract middle point, and using this middle point, we're going to remove overlapping line. For that, I will take cal duplicates, remove all overlapping points, but I'm going to take I output, set here leave 1, and here in the I output we have the integer numbers of all points that are stay in the output. So I'm going to take these numbers, place in the index number of the list item, and the list will be the segments of the point lines. And now here instead of 36 lines we have 18. And in the next step, I'm going to offset each line in both directions. This line will be offset in two directions. This guy here offset also. So for each line, I'm going to use offset curve. And in the offset distance, we need to place two values, positive and the negative value. Offset distance can be 2. And let me check here. We have single branch with 18 items. For each item in the list, we need to create two values. That's why I will create two branches with entwine component, and first input will be positive 2 and the other input will be negative 2. I will place it D. You can see that each line is offset in two directions. If I take a look at the data structure, you can see it here, but I want to create data tree with 18 branches. Inside each branch 2 items, because here we have 18 items in the original list. So for instance, for this line here, that is, let's say, placed in the branch 0, we'll get 2 lines. So these 2 lines will be placed in the branch 0. So first, I'm going to simplify a list, and I will use shift pad. If we take a look, by default, offset factor is -1, but this is not what we want to get. We get here 2 branches, inside each branch 2 items. So instead of -1, we should place 1. If I place offset factor 1, we'll get 18 branches, inside each branch 2 items. Once we get this one, we can create closed point line. I will use component to connect curves, but if I take these 2 guys and place it here, you'll get a weird result because they should have opposite directions, and in that way can be easily created closed curve. But if these 2 guys have the same direction, we'll get this kind of result. To flip one of these 2 curves, I will take a list item, go here and press on +1, and one of these 2 curves I'm going to flip, and I will merge them once again. Once they're flipped, I can create a closed point line. And here in the G input, we should set 0 because I want to get straight connections. In the next step, I'm going to flatten the list of point lines, and I will use region union. So we'll get a single region. I want to separate these segments of the region union of the output in two lists. The first list will be the lines that are equal to our offset factor multiplied by 2. All these lines will be placed in one list. Another set of lines will be placed in another list. Before we get to that part, I want to avoid these merging ends. So this is okay. This part are fine, but this part I want to modify. To modify this, I'm going to set, instead of 15, I will set here to 15.3. And now each end of the polyline are separate. Once we take a region union, explode these polylines, I will take segments and I'm going to calculate its length. Don't forget to flatten the list. And I will check if the length is equal to the offset factor multiplied by 2. Why it's multiplied by 2? We know that this distance is 2. If we multiply 2, we will get the full length of these lines. I will use component dispatch. Here we get the pattern, place it here, and we get A and B lines. Actually, I'm going to place here unequal. In the B output, we should get all these lines. But you can see that here we have only a single line, because if we take a look at these two lists, here we have number 4, and here we have 4.0, 4, once again, 4.0, 4.0. So instead of having 4.0, we should get only 4. So I'm going to round all these values using expression. And the expression, I will type round x, comma 4. So I'm going to round this into 4 decimals. And I will take this length, connect with the panel, and you can see here we don't have any more 4.0. Okay, I'll place it here, and in the B output we should get all these lines that we need. In the A output we have all the lines that are not equal to 4. Now I'm going to take all these lines from A output and we need to sort them in a right order. These two lines, for example, should be placed in the same branch, let's say 0, because they are related with this original line. Then these two should be placed in the branch 1 because they're related to this guy, and so on. So in order to place them in the correct order, I will take these lines, so these curves, and I will find their middle point. And I will also find middle point of the lines from the output A. Turn off all the rest. Maybe we can turn this on. I'm going to use component closest points. So these points, I'm going to visualize them. Okay, these blue points needs to be pulled to their two closest yellow points. Based on their index number later on, we are going to sort the list of lines. Let me show you how we can do this. First, let's use component closest points, and these blue points I'm going to pull to these yellow points. And I'm going to find two closest points. We need I output. So, for instance, I'm going to use point list. So for instance, point 0 has two closest points from the yellow, which are 0 and 30, and we can see it here. Two closest yellow points from this guy here are 7 and 29, and we can see it here, 7 and 29. Point 2, two closest yellow points are 28 and 33. Once we get these index numbers, I'm going to use them, and I will also use lines from the A output and place it in the list len. We don't need this anymore. Instead of having one single branch with 36 items, we have 18 branches, inside each branch 2 items. And let's take a look. In the branch 0, we have these 2 lines. In the branch 1, we have these 2 lines, and so on. But what I want to do, I want to create a list of lines in each branch. So this will be line with the index 0. This will be line with the index 1, and this one will be a line with the index 2. Right now, we have only 2 lines, this guy has index 0, this guy has index 1. So we need to insert this line in the position 1. So insert items, this will be the list of lines. In the position 1, I will insert these curves, but don't forget to graph this one, because here we have 18 branches. Here we should get 80 branches as well. All right, now we have 18 branches, inside each branch 3 items. Let's take a look. So these 3 lines are placed in the branch 0. And if I use a loft, we can create a surface. As we don't get the result that we want with default settings, I'm going to use loft options. And in the adjust input, I will type true. So I will use toggle boolean. And in the type, loft type, we should set straight, because I want to get straight edges, which is number 3. I will use these loft options and we get the result that we want. Now I'm going to convert this surface into mesh. So we'll use component simple mesh. Once we get 18 meshes, I want to join and weld the mesh. I can use component from the Werebird plugin, which is called Werebird join mesh. And don't forget to set true in the W input. Once we get welded mesh, I can subdivide this with Kangaroo component refine, and the level of subdivision can be, let's say, number 3. All right, let's go to perspective mode. I'm going to use Kangaroo to create tensile structure. So let's go here, use solver, and we need goal objects. The first goal I always use show, because I want to visualize the mesh that is going to be transformed. And also we're going to use this mesh later as a first output in the list. This is the first goal. I will use endFine, place in the 0 branch. We'll flatten this later on. The next thing is to create anchor points. Anchor points should be vertices of the mesh that are placed on these lines. This is the moment when we need to use lines from the output B. These are the lines that we need. I will extract a naked vertices, which you can find it somewhere here. Naked vertices, place in the mesh. Here we get naked points, but here we get all naked points. I don't need all naked points to be anchor points. I just need points that are placed on these curves. So I will use component pull point, and I will pull them to these curves. If the distance is 0, I will use only that point. So first I will use round. So I'm going to round these values, and if the value is equal to 0, I'm going to use these points. Call duplicates, take these points, and here we get the point that I will use as an anchor point. And here I will place in the P. Strand I will keep by default 10,000. I will place in the 1. So if I place it here, we will not get, I think, any different result that we get right now. In the next step, I want to add Vertex Loads. Basically, I want to modify the mesh in order to create tensile structure. So this will be the mesh. And here we can set the strength. We can see that all vertices go into infinity because we need to set mesh strength. So I will use component edge length, and here we can set length factor and the strength of the mesh. Don't forget to add one more input. I will place it here, and I'm going to reset the solver. Take the output with index 1, only mesh. You can see that I want to create the load into opposite direction. So that's why in the strength I should set, by default it's set to -1, but we need to set a positive value. Let's set here 0.0, and we get quite nice result. But I want to modify also edge length. By default is set to 1. I'm going to type here, let's say 0.1, and the strand by default is 0. we can keep it like that. And the next mesh that I'm going to add is related with the mesh edge length. You can see how this edge length is way smaller than this one here. So I want to avoid this, because later on, if we want to fabricate this structure, it will be so difficult to create this part with a short edge length. So there is goal, this guy, length line. So I will take mesh edges, and I will use also both naked and interior edges, place it in the line. Basically, with this goal, mesh edge length will tend to be the same as the average length of all these edges. Let's say length can be 0.5, and the strength can be, instead of 10 by default, we can set to 1. And once we add one more goal, you will see the difference with this short edge length. Now it looks way better to fabricate. Alright, so this is first part of the tutorial, how we created this mesh using Voronoi and Kangaroo. Now we are going to use another plugin, which is called Stripper. Basically, with this plugin, we can separate and divide this mesh into stripes, which will be later on used to fabricate. So first, I'm going to use this component get mesh topology directionals. Now we get U and V directions. I'm going to use curves from the output V, and I will take these curves to create mesh stripes. So there is component which is called the strip via directionals. This will be the mesh that we're going to strip, and these are the directionals. I will turn this off just to visualize these stripes. You can see how mesh is separated. So we get here, let me check, 80 stripes from a single mesh. All right, in the next step, I'm going to subdivide this mesh with also a stripper plugin. Here we should place one level of subdivision, and type should be 1 instead of 0. So I want to keep fixed naked edges. In the next step, I'm going to lift middle vertices of each stripe. So we can do this with component lift mesh vertices. In the S input, we should place false, because if we take a look here, false means we're going to lock non-boundary points. And here we need to set the distance. I want to move them in opposite direction, so that's why I will use negative direction. In the next step, we are going to randomly map each mesh face with the certain tiles that we create. You create these tiles on your own. I already created these 4 tiles. I will use geometry to reference these 4 guys. But in order to map this to each mesh face, we need to convert each mesh face to a surface. So for that, we need to use component face boundaries. Basically, from each mesh face, we created a closed point line. We know that these point lines has 4 control points. We can extract them with the discontinuity, and with the list items, we can extract each point. I'm going to zoom in here, and I will add 3 more outputs for 3 more points. Now we can create 4 point surfaces, connecting each point with each point of the surface. And you can see how we created 9,216 surfaces. Now I'm going to flatten this list of surfaces, and I want to basically divide this list of surfaces into 4 lists, because we have 4 different tiles. I don't want to map them in certain order, they should be mapped randomly. I will use component shift pattern, and the pattern will be 0, 1, 2, and 3. Uncheck multiline data, and this list of 4 values I'm going to repeat as many times as we have surfaces. So we need first to calculate the number of surfaces with the list length, and here we created this pattern until it reaches the maximum number of surfaces, which is 2215 index number. Now I'm going to shuffle this list of values from 0 to 3. If we set to 1, it means it will be fully shuffled. And in the as input we can set iteration. Once we get shuffled list of values, I can place in the P input. Here we get the warning. This is why we don't have the output 2 and 3. If we add 2 and 3, we'll not get warning anymore. And if I take outputs from 0, we get this list of surfaces. 2, 3, we can use and twine to place each list of surfaces in a different branch. Don't forget here to add one more input because we should get 4 branches. All right, and these are list of surfaces that should be placed in the component surface morph. This is very similar with the flow along surface component from Rhino, and these surfaces will be placed in the surface to map onto. So we need 5 more inputs. The first one is geometry 2D form. Here we get geometry 2D form. But keep in mind that we have 4 branches, so each of these tiles should be placed in a different branch. But there is one more step that we need to define, because I don't want to map them in the same orientation. Maybe sometimes I want to rotate this guy by 90 degrees, this guy I want to rotate by 180 degrees, this one will be rotated, let's say, by 270. To also create even more interesting result, we can rotate these tiles, and the point rotation plane will be, if we can get, if we use boundary box, and we can use volume, or we can use area because this is flat box. I'm going to use center, and this will be center of rotation. And we also need to define the angle. The angle of rotation will be 4 angles: 0, 90, 180, and 270. Uncheck multi-line data and place it here. Also, don't forget to set degrees instead of radiances. Click on A and click here on degrees. So now we have 4 branches. Inside each branch we have 4 items. So let's say here in the branch 0 we have 4 positions of this tile. In the branch 1 the same logic. But here we need to have 9216 values. So to match with the data tree that we get in the input, I will use component longest list. So 9216. I will use here also wrap, which means in the B output now we get the number of items that we need. We have matching data tree. I also want to shuffle the list of surfaces. Super random, I will type 58. All right, and this I am going to place in the G input. Now we need R input, which is reference box to map from. So we can get these reference boxes. Keep in mind that for the reference boxes, we also need to have 4 branches, in each branch 9216 boxes. So I will take, let's say, these bounding boxes, and I will use box rectangle, this one, as I know that we have already boxes. And here we get 4 branches, in each branch 1 box. I will set here from 0 to 1 because we need here a domain, and I'm going to repeat this guy 9260 times. Here we get 4 branches, inside each branch the same number of items as that we have here and here as well. Once we get reference boxes, we can place in the R input. Now we need U, V, and W. Basically the tiles that we have, they need to cover fully surface. So that's why I'm going to place from 0 to 1 in all 3 inputs, U, V, and W. I'm going to disable this for now. But don't forget to reparameterize surface to map onto. If you don't reparameterize, this 0 to 1 will not work. We managed to randomly map these 4 tiles. If you have, let's say, 6 tiles, you need to have a pattern from 0 to 5, and here you will get 6 branches. If you want to color these surfaces, you can go further with this script. Basically, I'm going to explode this data tree, match the outputs, and place all these map tiles in a single branch. So we use combine. And as a result, we have a single branch with 9,216 surfaces. We'll turn this off. And if you want to color these surfaces based on the gradient, I'm going to use mesh that we get here once you lifted vertices. And I'm going to weld and join meshes with the Weaver plugin. I'm going to disable this for now. Don't forget to set true in the W input. Also, I will use face normals to extract center of each face. And I will use mesh edges to extract naked edges of the mesh. I will use E1 output. I will join these curves. And I'm going to pull the center of each face to the closest naked edges. So I'm going to use component pull point. These guys I will flatten and pull to their closest naked edge. Alright, based on these distances, we can create the gradient and color the surfaces. So first I will use bounds to extract minimum and the maximum value. So I will use bounds, then deconstruct domain, and then we can create gradient. Preset, I will use this default preset, but you can create a gradient by yourself. So this is start, and these are the, basically we should get 9,216 colors, and we can use these colors to color the surfaces. And here we get the final result. The extended version of this tutorial, which is available on our Patreon page, will cover how to prepare this project for digital fabrication. We'll be using a plugin called OpenNest to organize and nest all the individual pieces. Then we'll create a numbering sequence so we know exactly which part goes where. And lastly, you will find out how to create flaps for the pieces so they can be attached properly to one another. You can use this method to apply to any project you're working on. With this extended tutorial, you will get access to all our other extended tutorials and project files, so you can practice on your own. The link is in the description. If you'd like to know exactly how to create complex projects like these, and if you're interested in step-by-step learning approach starting from zero, make sure to check our Grasshopper Complete course, where you'll find over 60 hours of video material structured in a form of video library, covering in depth more than 500 Grasshopper components through practical examples. And you'll have access to us personally, so we can answer all of your questions right away. The link is in the description.